So prove that for even powers of sine of x, we got the integral from 0 to pi over 2 sine of 2n, sine to the power of 2nx dx is equal to, we have 1/2 times 3 over 4 times 5 over 6, goes on and on and on, and then we have that eventually is going to give us 2n minus 1 over 2n times pi over 2. So we have to prove this. Okay, so let's go ahead and prove it right now. We are going to be using mathematical induction to tackle this problem. So let's go ahead and see how that looks like. We got here the solution. Let me go ahead and change color to blue. Okay, so the first step in doing a mathematical induction proof is we will start with our basis. The basis step. There's two steps. There's going to be the basis step and then there's going to be the induction step. So we're going to have to start with our basis step, and we are just going to basically just see if this statement right here, this function, this statement is true for the n values. So we're going to start with n equals 1. So basis for n equals to 1, just plug 1 in. We're going to see if this is true for the n values that we choose. So let's start with n equals 1. So that will be the integral from 0 to pi over 2 sine, when n equals 1, this is just the second power, x dx is equal to. So when n equals 1, we're going to be using this, all right? And obviously this too, but let's see how that looks like. So we have 2n, n is 1, right? So 2 times 1 minus 1 over 2 times pi over 2, that will give us, that is going to, oops, sorry about that. No, go away. I don't know how to do that. All right, so that is going to give us, for n equals to 1, it's going to give us pi over 4. So this checks out. So the formula, so this formula that we have here holds true for n equals to 1. Okay, so now that we found out that it holds true for n equals to 1, this is true, by the way. So if you were to actually integrate this, which I'm not going to do to save time, that's going to be the answer. So let's see if it works for n equals 2. So this will be the integral from pi over 2. We have sine, that's going to be 4x dx is equal to, again, 2 times 2 when n equals 2 minus 1 over 2 times pi over 4. That is going to be, when we're doing this, pi over 4, sorry about that. Ignore this. It's not pi over 4, it's pi over 2. Pi over 2. So we actually have this. So 2, that's 4, that's 3 over, sorry about that. 3 over 4, right? And look at this. This is 3 over 4. We have 3 over 4 right here, right? So that holds, so far it's holding true, but we need to multiply by this, right? Because all of these are being multiplied, right? They're just fractions, so it's like 1 over 2 times 3 over 4 times 5 over 6 and so on and so forth. But since we used, hold on a second. Since we use n equals to 2, this is our second term. So we're going to, and that's what we have here. So we're going to have to multiply our 1/2, and obviously we're going to have to multiply our pi over 2. So we have, sorry about that. We have, okay. So 3 over 4 times 1 over 2. Remember, we need to multiply because it's like a sequence, right? Okay, so we have to multiply by 1 over 2, and then we have to multiply by pi over 2, because this is always multiplied by pi over 2. That is going to give us, let's see, for n equals 2, that is going to give us 3 over 16 times pi, and that holds true for n equals 2, so that is valid. So let's just do just one more. I like to do one more. Instead of just 2, we can do one more. So n equals to 3. So for n equals to 3, let's see what we got. The integral of 0 to pi over 2 sine 2 to the power of 2 times n equals 3. That's sine of 2 to the 6th power x. That's an even power, right? So dx is equal to, again, since we are in the third n term, we're going to multiply this one, we're going to multiply that one, and we're going to multiply this one, right? We're going to multiply these three terms, and we're obviously going to multiply by the pi over 2. So doing this whole, plugging that into our formula, we should be getting, let's see, what are we going to get? We're going to get 1/2 multiplied by 3 over 4, which is following our sequence, right? So far it's looking good. Times 5 over 6. Yep, it's following our sequence. Lastly, multiply by pi over 2. So 1, 2, 3. So for n equals to 3, we're going to get 5 over 6, and obviously multiply the rest of the sequence in your pi over 2. So make sure you do that. That in total is going to give us, what is that going to give us? That's going to give us 5 pi over 32. And again, if you do the integration, that checks out, so that is valid. So now that we found out that this is pretty much valid, we are going to assume, okay, we're going to assume something. So now we're going to make our assumption. So assume, we are ready to make our assumption. Assume that for what? Assume that for any, let us name this value, basically this value, let's name it k. For any k that is greater than or equal to 1. So assume that for any k can just be like any integer, right? Any whole number. For any k that is greater than or equal to 1, the integral of 0 to pi over 2 sine, we're going to replace our n with k. So sine of 2k x dx is equal to our sequence of 1 multiplied by 3 multiplied by 5 ... I'm going to have 2k. Remember, you are going to substitute your n for a k. K is going to be any integer, right? This is going to be our assumption. We're going to have to prove, or we're going to have to assume that this is true, and we're going to have to go ahead and support it. 2k over pi over 2. So this is going to be your assumption. Assume that this statement is true. If this statement is true, then, and we have integers of n equals to 1, 2, 3, 4, ... If this statement is true, then this has to be true, right? So if this statement is true, let's go ahead and prove or see if of n equals to k plus 1 is true. We're going to have to see if that's true, right? Because look, we have n equals to k. K can be an integer, right? So k can be like 0. What is there? K can be like any value, right? That, and also integers, right? So k can be 0. So when k equals to 0, n equals to 1. When k equals to 1, n equals to 2. When k equals to 2, n equals to 3. So is this true? We are going to see if this is true, right? So since we are going to see if k plus 1 is true, because if this here holds true, as we have seen here in our basis step, if that holds true, then that means this has to hold true as well, which we are going to have to see. So we're going to have to see if that even holds true. So let's go ahead and consider. Let's go ahead and consider. Now we're going to have to consider k plus 1. So consider k plus 1, which is this. Consider k plus 1. So consider. when we add a 1 to k, the integral of 0 to pi over 2 of sine of 2 times k plus 1, consider when n equals to k plus 1. Do your, what do you call it, your distribution. That is going to be sine to the power of 2k plus 2x dx. That is going to equal to, we are going to basically we're going to basically substitute n, k plus 1 for n. So that is going to be, so what we have here, substitute k plus 1 for that. So we have 2 times k plus 1 minus 1 times 2 times k plus 1. And that we're going to multiply it to our assumption. So multiply this to your assumption to see if we get equivalent statements. So this is our original assumption. 0 to pi over 2 is sine 2k x dx. So multiply that to your original assumption. So this is your original assumption. And we're going to have to multiply, obviously multiply your k plus 1 when n equals to k plus 1. You multiply that by this, and we're going to see if these statements hold, if like the statements hold true. So so this is going to equal to, let's see, so this is going to be equal to 2k, do your distribution, do your algebra. So that's going to be the 2k plus 1 over 2k plus 2. This is just like to simplify things a bit. And okay, so that is going to, remember what we said, what is this equal to? So this part that we're multiplying, we're going to be multiplying by, so remember, this here is equal to this. So we're going to multiply our 2, when n equals 2k plus 1, 2k plus 1, sorry, when n equals k plus 1, I'm sorry, have I even seen 2k plus 1? Sorry. When n equals k plus 1. So when n equals k plus 1, that stuff, we are going to multiply our original assumption by it. So that is because this is a multiplication sequence, if you want to call it that. This is multiplication, so we're going to multiply. If it's adding, then we're probably going to add it. So 1 times 3 times 5 dot dot dot. Our original assumption, remember, it's 2k minus 1 over 2k. So 2k minus 1 over 2k. That is going to be 2 times 4 times 6 dot 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 of pi over 2. Don't forget your pi over 2. Okay, so now just multiply across. But before you do, when we multiply across, try and keep it in like this format. And you'll see why. You'll see why pretty soon. This is just like to simplify things, just for the sake of simplicity and for it to look good. But this here is for, you'll see why I want you guys to multiply by this format. All right, so let's multiply. So that equals, oops, 1 times 3 times 5 over 2 times 4 times 6. I don't know why it keeps doing that, but dot, 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 dot. When we multiply across, we have 2k minus 1 over 2k, remember that. And then we have, in brackets, multiply the numerator across, we have 2k, oops, parentheses plus 1 minus 1 close brackets, and then at the denominator we have 2 times k plus 1. Okay, so this is basically just this. So that is why I want you guys to multiply it like that. So make sure to multiply this because it's actually easier to see. I'll show you in a minute. So now that we have our what? Oh yeah, pi over 2. Don't forget your pi over 2. So now that we have this statement here is basically the same thing as so this statement here that we have here, that statement that I just put the whatever you call that on. So this statement here is basically the same thing as our original statement, which is this, as our original thing that we want to prove, right? It's the same thing. It's just a different format. It's the same thing when we let n equal to k plus 1. So that's the same thing. And I'll show you in a minute why if you can't see it yet. But that's the same thing, and that's what we want to prove. So we pretty much proved it by induction. But check this out first. So so this is all multiplication, right? All of this is multiplication, keeps going on and on and on. All of this is also the multiplication, keeps going on and on and on and on. So check this out. When we let k equal to 1, that's going to be 2 minus 1, that's 1 over, when we let k equal to 1, that's 2. And then this is pretty much basically the same thing as, look, checks out, right? Checks out. When n equals to 1, in this case, when k equals to 1, when k equals to 2, k equals to 3, sorry about that, come on, k equals to 3, it checks out. Because look, we have this and we have that, it checks out. So just plug in whatever value of k you want. And this here, let me just erase everything. Just explaining right now, so hopefully you guys see it. And this here, this part right here, it's the same thing as 2n minus 1 over 2n times pi over 2 when we let n equal to k plus 1. So it's the same thing, just in a different format, right? So this checks out. We have proved this by induction, so therefore the formula holds true for n equals to k plus 1 and for all n which is greater than or equal to 1 as shown by induction. And that's it. It's basically it. That's how you prove it. So yeah, this is just proof by induction. If you have any problems with induction, then I suggest you review induction before tackling proofs like these. So yeah, that's it.